everyone. I'm Jiaxin from Chinese University of Hong Kong. So it's my honor to be here introducing our work in Endo3R, unified online reconstruction from a dynamic molecular endoscopic video. So 3D reconstruction from endoscopic data is a challenging task and a crucial task to provide intuitive and precise spatial perception for surgeons. And it could help expanding the range of inspections, capturing intricate and anatomical structures. So estimating the scale-consistent 3D structures of monocular endoscopic video is also very challenging in the dynamic real-world surgery. So, for example, we can have challenges like monocular scale ambiguity because we only have the single view which lacks multi-view constraint. We also have the homogeneous and reflective surfaces in the images, which will be hard for us to make robust matches to have good triangulations. And we also have deformable tissues and moving instruments, which is due to the breathing, heartbeats, and some interventions, making it hard to establish static assumptions for reconstruction. So all of the factors will lead to this ill-posed and under-constrained problem, and lacking multi-view constraints and static assumption. So the question is, how can we estimate scale-consistent 3D structures from monocular endoscopic video? So we want to achieve this scale-consistent depths compared to this inconsistent depths to achieve multi-view consistent and also have good temporal smoothness, also remain the stable scale without any arbitrary shift. So for the previous method, like traditional method, structure for motion or B-SLAM, they have rigid assumptions, so they will get failed in such dynamic reconstruction, and they also fail in these textureless and homogeneous surfaces. And for the monocular depth model, and like transfer DA to transfer the depth anything V2 to the surgical scene, they will have they will get failed in the surgical scene and have inaccurate relative geometry. There is still a domain gap between the general scene and the surgical scene. For the multi-stage depth model, like scale-aware depths and EndoDAC method, and they have multi-stages to reconstruct the scene and to achieve scale-consistent depths. So there can be like some requiring prior information, like the two sides, which is not always available in the real-world surgery, and also there can be like some error accumulation and requiring offline optimization to achieve long-sequence reconstruction. So in our work, we present Endo3R as a unified 3D surgical foundation model to achieve online scale-consistent reconstruction from molecular endoscopic video. We don't require any prior information or extra optimization. So as shown in this graph, we take the unposed and uncalibrated video as input, and our Endo3R could achieve a feed-forward output to predict the 3D global point maps. And we can achieve almost 20 FPS on a single RDX 3090. And then we could predict like video depths and camera parameters, including intrinsics and extrinsics, and achieve dense 3D reconstruction, like point maps. And we can also apply our method to some subtasks, including this dynamic video depth estimation and long-term online reconstruction, and also sparse view reconstruction, which means the overlapping between the consecutive frames is limited. So specifically, we have proposed an ensemble-aware dual memory mechanism. This is to expand the stereo reconstruction ability to the long-term online reconstruction. And we can also achieve higher robustness and accuracy. And we have also proposed a self-supervised scheme to achieve, to introduce our method to scale up to more surgical data sets without ground truth poses, depths, and intrinsics. Because for the surgical data set, we know there is a data set scarcity, so only limited data sets have the ground truth poses and depths for training. And specifically, here is our network architecture. We take the unposed and calibrated video as input, and we input into the VAT encoder to encode into the image tokens. So to achieve the online reconstruction, we apply a attention-based memory mechanism that is to take every new images as input and then query this in the historical memory, which stores the historical case and the values. And then after the querying, we can get these fused tokens, and then we can conduct the cross interaction between these these fused tokens and the current token to predict the 3D geometry. However, in this process, we observe that it's not necessary to store all the tokens, like some highly dynamic tokens, the regions with some tools into our memory buffer, which will influence the accuracy. So here we propose uncertainty-aware dual memory to include both long-term spatial buffer to save the keyframe tokens with stable 3D information, and also the short-term temporal buffer, like to storing some neighboring frames to maintain the temporal consistency. And we also have an uncertainty check to eliminate noisy tokens of transient objects and occlusions, and this could help us to enhance the global consistency and robustness. And finally, for the regression, we adopt the DVD architecture as our head to predict the 3D point map and associated confidence map. And we can obtain the intrinsic, extrinsic, and the local depths during the post-processing. So to achieve the self-supervised training, we adopt this, we present this dynamics-aware flow loss to achieve the self-supervised training by decoupling auto flow into post-induced motion and point map-derived scene flow. So specifically, we first adopt the raft model to derive the optical flow to indicate the 2D correspondence between the consecutive frame. Then starting from this 2D correspondence, we can obtain the 3D correspondence, and then we can obtain this scene flow. And then from our estimated poses, we can obtain this post-induced flow. Then after combining them together, we can get this estimated optic flow and then apply the dynamics-aware loss between our estimated flow with the pseudo-GD flow, which is from the off-the-shelf model. And for the datasets without ground truth depths, we obtain the pseudo-GT depths from off-the-shelf model, video depth anything, and then apply this scale invariant depth loss to supervise the estimated depths. And we also adopt this confidence-aware loss from Endo3R for the supervised training. So this is our total loss. So specifically, we use these datasets for both the datasets with ground truth depths and poses, and also the datasets without either depths or pose. So for the datasets with the ground truth, we use them for training and evaluation on the scene 8 and 9 of the scale dataset. For the dataset only without the full labels, we use them for self-supervised training, and we adopt Haomin dataset for zero-shot evaluation. So this is our evaluation results. We compare with both surgical methods and the general method. And it shows that our method could significantly outperform all the previous method and also maintain a competitive speed, like 19 FPS. And we have also conducted zero-shot test on the Haomin dataset, which means our method hasn't been trained on this dataset before. And we can also achieve the best performance. And we have also conducted post-estimation comparison on this dataset, on the scale dataset, comparing with previous method. It shows that our method also achieves the best performance. And we have also conducted ablation study to show the effects of different components. And it shows that with all the modules on like uncertainty-aware memory and the self-supervised training, our method could achieve the best performance. So this is our qualitative results. We compare with previous surgical method, and it shows that our method could achieve both the fine-grained details and also the good scales comparing to the ground truth. We have the similar color like indicates the good scale. So this is our qualitative results on the long-term reconstruction. We can also maintain a stable, 3D consistent reconstruction result here. And we also visualize our estimated video depth here to show a smooth and fine-grained depths without any flicker or jump. And this is our visualized estimated point clouds and poses on the dynamic reconstruction. And we also apply our method to some downstream tasks like 2D 3D restoration and navigation from molecular video. So here we have first used the city model to extract some like point cloud, ground truth point cloud, and also use the rendered images as input to Endo3R to predict some poses and point clouds, and then use lab to achieve global bundle adjustment to enhance the accuracy. And then finally, we can achieve this, this city augmented navigation performance to align our reconstructed result surfaces with the city very tightly. So in conclusion, we present Endo3R as a unified framework for online 3D reconstruction from uncalibrated videos. And our method could jointly estimate pose depths and scene geometry in a single stage without any multi-stage pipelines or offline optimization. And our experiment could also show our superior performance in depth estimation efficiency and the geometry and generalization ability, and it also provides a foundation to our future research in surgical scene understanding. So, but we also find there are some limitations in our method. For example, if the given sequences are too long, our method will have some like drifting artifacts. So it's also our future work to enhance our robustness and accuracy under such scene. So thanks if you are listening. So our poster board is on A290 this afternoon. So if you have further questions, welcome to contact with me. And also this is my WeChat and linking. Welcome to add, and we have a further talk. Thank you.